So in this video I'm going to go through some of the questions that you had for homework, the first of which was question 213. Now I hope you've tried these questions before watching the video and you're just using this as an opportunity to check your answer. So 213 gives us a graph about a running session that Alice and Bob have done from one town to another town. You have a diagram and you need to find out where they are at different points in time and write a description of their journey. So the first thing that we can see is that the time when the line starts is a quarter of the way between 10 and 11 o'clock. So I'm going to write A for Alice and B for Bob. Started their run at 10:15, a quarter of the way between 10 o'clock and 11 o'clock. They ran until where the line continues going upwards, that's them making progress over time. So they ran until 11:45. And actually we can see here how far they ran, because where they started was at 3 kilometers, and where they were then at 11:45 at the restaurant was just before 12 kilometers. So they ran just under 9 kilometers, so that's from 3 kilometers to just under 12 kilometers until 11:45. Then they stopped. And we can see that by the flat line that we have whilst they're at the restaurant. Of course, it makes sense that they stopped at the restaurant. But the flat line means that time is still passing, but they're not getting any further away from where they left. So the only thing that we can read here is how long they stopped for. So from 11:45 until 12:45. So then they stopped for an hour until 12:45. After that, they ran on for 15 minutes. You see the line goes up a little bit slightly until they reached the viewing tower, where they rested for 30 minutes. After leaving the viewing tower, they ran for a further 15 minutes until they reached their destination. And the destination, we can see, is at 17 kilometers. And as they left from 3 kilometers, that means that they ran a total of 17 minus 3 kilometers, 14 kilometers. Overall, they ran 14 kilometers. And the total time they took was from 10:15 until 1:45. So 3.5 hours. That's all I'm expecting for you to answer in 213. You could, if it's something you've done before, find the gradients of the lines and look at how fast they ran when they ran, but I don't expect you to do that, and gradients are something that we'll talk about later. So let's move on to the next question, which is question 215. So here we have a phone contract. And we need to say what G of 1000 means. Now it says that G is the cost of speaking for T minutes. So our function is g of t, which is the cost of speaking for t minutes. So g of 1,000 is the cost of speaking on the phone for 1,000 minutes. Therefore, g of 1,000 is equal to 7 means that it costs €7 to speak for 1,000 minutes. And 215 is then done. Let's move on then to 216. So, we have a specific place on a specific day. At 4 times, there's a temperature that's measured, and the temperature is given in terms of the time t. It's worth noting here that t is your independent variable, and the temperature t, big T, is the dependent variable. This is normal. This is the normal state of affairs where the time is the independent variable. And we have then the temperature T depending on that. So, we have a couple of things to do. The first thing to do is to read off T of 18, which is the temperature at time 18, so 6 o'clock, and that's of course 2. Also T of 21, which is of course the time at 9 o'clock, the temperature at 9 o'clock, sorry, which is then 1 degree. Next, we need to find the T for which the temperature at that time is 3. This means that at this time, when the temperature is equal to 3, we can read from the table that that's time 15. So that's our answer there. Finally, we need to find the small t for which the temperature is bigger than 2. And we have 2 times at which the temperature is greater than 2. It's 3 degrees at the time of 15 and 4 degrees at the time of 12. So we have 2 solutions. We have T is 12 and T is 15. So hopefully you got those 3 correct. Let's move on to the next one, 217. Now in 217 we have 3 different relationships, and the book asks us, can they be considered as functions? And the answer for all 3 is the same. Yes, they are all functions. They can all be considered as functions. Because we have always an independent variable. So in the first one, that's the natural number. In the second one, that would be the velocity or speed of the vehicle. In the third one, it would be the age in years. And they all have then a dependent variable that depends on that independent variable, and each of the values of the independent variable are only assigned to one of the values of the dependent variable. So yes, we have a unique mapping where each x value is only mapped to one y value. Of course, in the first one we have some y values that occur for different x's, so for 2, 3 and 5 the y values are the same, but as we mentioned in class, that doesn't matter. As long as each x only gives us one y, then that's absolutely fine. So, in 218, the table should be completed as the independent variables in order are V, A and R. Now this first one with V, this is a little bit of a strange one because that has a dependent variable of time t. And I said that normally t would be the independent variable and the velocity or speed v would be the dependent variable. However, that might be normal, but doesn't happen all the time. So t can be the dependent variable, but this one here is a special case. So you have the one that you put in, the independent variable, these three, and this is what you then get out, or what's assigned to each one of those. So our final question, 219, involves a graph, and I've done a little sketch of it here to be able to show you how to read off the different values that you need. This is an important skill that often comes up in the Matura actually. It might seem quite simple, but it's something that is often asked within the exam. So, first of all you need to justify that the graph gives a functional relationship. And of course it gives a functional relationship because each x value is mapped to only one y value. So that's our answer for part A. Or part 1, sorry. For part 2, how big was the average number of children in the year 1978? So we need to go to the year 1978, which would be, I think it's about here in the book. You've got two little lines after 1976. So you find 1978. You come up in a straight line that's at right angles to your axis. You find the point on the line, and then you use your ruler to go across to find out what the corresponding y value is. So what's this value here? And you should find that it gives you a value of 1.6. So each family had an average of 1.6 children in the year 1978, or each woman had an average number of children of 1.6. So, number 3 asks us to do something very similar. K of 1990 is the number of children per woman in 1990, so we would need to find 1990 here. Let's say here. Go up. Mark it, read across again, and you should find that that's equal to 1.5. K of 2010, again something very similar, find 2010, go up to the graph, mark it, and read across, and for that one you probably will need your ruler, and you should find that that's about 1.4. children per woman. So it seems that it is decreasing a little bit. However, it does fluctuate. Finally, we need to find the year, J, for which K, that's an H, K of J is equal to 2.4. So we need to find the year for which the average number of children per woman was 2.4 children. So if you go to 2.4 on here, which is going to be about there, read across, and you'll find actually that your line across cuts this graph twice. So you should mark both of those points, Then get your ruler